Students, so what we want to do is to start to look at thermodynamics, and this is a basic introduction of some of the concepts in thermodynamics. Now, the topics that we need to cover are heat and temperature, internal energy and pressure volume work, the first law of thermodynamics, heat capacity and enthalpy changes, and also to look at later on an application of, or the applications rather, of S's law when it comes to calculating enthalpy or enthalpy changes. Now, firstly, all chemical reactions require or release energy in some form or the other. So that's the first thing. That is the first thing. All chemical reactions require or release energy in some form or the other. Now, chemical reactions occur because of stability reasons. That is the thing. So if you have two reactants, all right, coming together to give you a product, this is generally because of stability reasons. That is, the two reactants might be a bit unstable, and so when they come together, the idea is that they would give a product which is more stable, lower in energy. Of course, this is not always the case. You could have two reactants coming together to give you a product which is less stable than the two reactants. Such reactions are non-spontaneous, and so they require the addition of energy to force them to happen. Now, as you can see here, and let me just get a laser pointer here. As you can see here, we have our reactions can be classified as either exothermic or endothermic. The thing is that all chemical reactions are both exothermic and endothermic at the same time. How is that possible? Well, if you consider a particular chemical reaction, you can imagine that in the reactants you have bond breaking occurring. Bond breaking is an endothermic process. It is a process requiring energy. Okay? Whereas in that same chemical reaction, you have bond formation. That is, bonds are being formed in the product or products. Okay? Bond formation is an exothermic process. So you see, in all chemical reactions have an endothermic aspect to them, as well as they have an exothermic aspect. However, the process which dominates will be the overall process. And so we say that, look, we'll say that, okay, the reaction is exothermic or it is endothermic. When we say that a reaction is exothermic or endothermic, we're talking about the net process or the overall process, meaning that more energy is released than that which is absorbed during an exothermic reaction. And so we say, okay, overall energy is released because more energy is released than that which is absorbed. In an endothermic reaction, right, more energy is absorbed than that which is released. And that's why we say, okay, the reaction is net endothermic. Okay? Now, you can imagine an energy profile diagram for an exothermic reaction would look like this one here on our left. That is, the reactants are of higher energy than the products. And so it's almost like rolling a ball down a hill. As the reactants are reacting with each other, right, to give you products, the product is lower in energy. So in other words, in order for the reactants to get converted to products, right, energy is released in going from reactants to products, because as you can see here, the products is of lower energy than the reactants. Of course, you might be saying then, what is this hump right here? What is this little hill? This little hill is called the activation energy barrier, and it is the minimum energy required for the conversion of reactants to products. Okay? For an endothermic reaction though, For endothermic reaction, the products is of higher energy than the reactants. Okay? That is, in order to convert the reactants to products, you have to increase the energy. When they combine, they must have enough energy to climb over this hill. So this is an endothermic process. It's a process requiring energy for the conversion of reactants to products. Of course, all chemical reactions require a minimum amount of energy to start off. And that minimum amount of energy is called the activation energy. It is the energy required to activate the reactants such that they can react. Okay? Now, higher energy means lower stability in chemistry. Alright? Lower stability means greater reactivity, as you can see I have written here. So for an endothermic process, you are producing products which are more unstable, or you could say then they are of lower stability than the reactants. Okay, so the products are more reactive. For an exothermic reaction though, the opposite is true. The products are more stable than the reactants. That is, you are producing something which is much more stable than the reactants. Okay? Okay. Now, what is energy? Now, for a simple definition, right? A simple working definition is that work is the capacity to, or energy, I should say. Sorry, energy is the capacity to supply heat or do work. All right? Energy is equal to heat plus work. All right? And it's a simple working definition. Energy is the capacity to supply heat or to do work. And that is the definition we will work with in this very basic course. Energy can be classified as either kinetic or potential. Kinetic being energy of motion, whereas potential is stored energy. Kinetic energy, often symbolized by EK, right? Like I just said, is the energy of motion, and is given by half mv squared. Half times the mass times the square of the velocity. And therefore, seeing that the unit for mass is kilograms, whereas that for velocity is meters per second. If you square meters per second, then you will end up with kilogram meter squared per second squared, which is equivalent to the joule, which is the unit for work. Kinetic energy is directly proportional to the mass and the velocity, or I would rather say the square of the velocity. And that is very interesting because measuring the temperature, for example, of let's say a glass of water, when you stick a thermometer in a glass of water and measure the temperature, you are actually by virtue measuring the kinetic energy. All right? And by extension, measuring the average velocity of the particles or the water molecules that are present and any other molecules that are there. Okay? Thermal motion, that will be discussed in another course. Potential energy is stored energy. All right? So energy might be stored as a result of the height of the object, or for example, let's say you have your cell phone on the desk versus on the floor. The cell phone on the top of your desk is of higher potential energy than that which is on the floor. Let me also give you another analogy for stored energy. Let's say you have an elastic band and you stretch that elastic band between your two index fingers. You will feel some sort of tension in the elastic band. So even though the elastic band is not moving, you're feeling some sort of tension in the elastic band. That is the potential energy, tension stored in the elastic band. Even though it's not moving, it is still and your fingers are still, but you feel the tension. That's that stored energy, potential energy. All right? Now, of course, like we said earlier, the unit of energy, the SI unit, is the joule. There are other units for energy, like for example, the calories. All right. Yes, and 1 calorie is equal to 4.184 joules, or 1 kilocalorie. All right, is equal to 4.184 kilojoules. But of course, we will be using mainly joules to represent our energy. Now, the law of conservation of energy, which is also the first law of thermodynamics, states that energy cannot be created or destroyed. It can only be converted from one form into another. All right? That is the first law of thermodynamics, which is also the law of conservation of energy. Now, the law implies that we can convert kinetic energy into electrical energy and even into heat energy, and all forms of energy, even sound energy, can come from kinetic energy, because that's what the law says. Energy cannot be created or destroyed, but it can be transformed. Right? It can be changed from one form to another. Okay? So you could have, let's say for example, you have a pot with water, and you are using a fuel, for example propane, to heat the water. The potential energy in the bonds of propane is being released, and that potential energy is used to warm the water. So the potential energy gets converted to heat energy to heat the pot, right? And the water will start to evaporate, and of course you have the water also moving. That's motion. You have also now the steam escaping, which you could use that steam to turn a turbine, right? And if that turbine is if you have a coil cutting a magnetic field, you could end up with electrical energy. So you have converted your potential energy, which is stored in the bonds of the fuel, right, into heat energy, into mechanical energy, and then into electrical energy. Right? The electricity produced by the turbine can then be used to operate an electric stove, a light bulb. Right? So you converted your potential energy all the way to light energy. You could use it to operate your radio, sound energy. All right? So the law is correct. Energy cannot be created or destroyed, but it can be transformed. All right? Now, thermal energy is the kinetic energy of molecular motion. All right? Thermal energy is the kinetic energy of molecular motion, which is measured by finding the temperature of an object. Like I said in about a slide or two ago, when you stick a thermometer into a beaker of water and you say that you are measuring the temperature, what you're basically checking is the kinetic energy of the water molecules, the motion of the water molecules. Basically, that's what you're doing. All right? So heat is the amount of thermal energy transferred from one object to another as a result of the difference in temperature between them. For instance, let's say you have a glass of water and that water is hot. All right? If you touch the glass, you will say, oh, the glass is hot. Why is that? It is because your hand is at a lower temperature than the water that is in the glass, or than the glass. And so what you find is that heat energy flows from the glass to your hand. And so you say, oh, the glass is hot. All right? If the glass was at a lower temperature than your hand, when you touch the glass, you'll say, oh, the glass is cold. That is because you have heat energy flowing from your hand to the glass. Okay? So heat is the amount of thermal energy transferred from one object to another as a result of a difference in temperature. Okay? Now, chemical energy is the potential energy of stored in chemical bonds. All right? Now, the first law of thermodynamics can be restated then as the total energy of an isolated system is constant. All right? So we have restated the first law of thermodynamics by saying the total energy of an isolated system is constant. Now, a thermodynamic system, because we keep mentioning the word system, a thermodynamic system is just the region of the universe, or some people would say the multiverse, that we are concerned with. All right? For example, gas in a container or a liquid inside a beaker. The beaker then would be our thermodynamic system. That is the region of the universe that we are considering. Now, everything outside the system is called its surroundings. Okay? The system is separated from its surroundings by its boundaries, and the boundaries can have various properties. Now, the boundary of a system may be its surface, for example, a drop of liquid, or the surface of a solution in a container, right? Or an elaborate wall of some kind that prevents certain interactions with its surroundings. Now, there are different types of systems. You have open systems, closed systems, and isolated systems. Now, the surroundings is everywhere else, like we said earlier. Open systems can exchange matter and energy with their surroundings, whereas closed systems only exchanges energy, but not matter. All right? Isolated systems, they do not exchange anything. They don't exchange energy and they don't exchange matter with their surroundings. So isolated systems do not exchange energy or matter. However, closed systems can exchange energy but not matter. Open systems can exchange anything. Okay, now we want to talk about internal energy and pressure volume work. Particularly, it is impossible to truly isolate a chemical reaction from its surroundings. And that is an interesting statement because it is true. It is almost impossible. It is almost impossible. There are some systems which are nearly perfect at this, nearly, but not perfect, nearly. For example, thermos. A thermos could keep water hot for several hours. So, for example, you could, if you have a thermos, or if you're familiar with a thermos, you could put hot water in the thermos from in the morning, like say about 8 o'clock in the morning, and it could stay hot for the next 12 hours. Right? Of course, it will be cooling, but the cooling is very little. So it stays hot for several hours. However, there is still cooling, indicating that the system is not perfectly isolated, because if there is cooling, this is an indication that there is some loss of heat energy. Right? So it's not perfect. So it's really difficult, or next to impossible, to truly isolate a chemical system. Now, it is important, however, that we are able to measure accurately the energy that enters or leaves the system. Right? We cannot isolate it totally or perfectly, but at least we must be able to accurately measure the energy entering or leaving. Now, the total energy in a system is called its internal energy. And this energy can be divided into two forms: kinetic, EK, and the potential energy. That's the total energy in a system. It could be divided into two parts, kinetic and potential. Okay? And we call that energy, the total energy in a system, the internal energy of the system. Well, it makes sense. It's inside the system, so it's internal energy. Now, for any thermodynamic parameter x, the change in that parameter is denoted as delta x. So we generally use delta to mean change. So if we're talking about x and somebody asks you about a change in x, then we say delta x, which means change in x. How do we calculate delta x? It is x final minus x initial. The difference between the final and initial states of x is called delta x. Delta just means change for us. Now, so therefore, a change in the internal energy, delta U, of course, because that's what delta means, change. So a change in the internal energy, delta U, is equal to U final minus U initial. Now, in some American textbooks, they tend to use E to represent the internal energy, but we will mainly be using U. Okay? Now, the loss of energy from the system, this makes sense. The loss of energy from the system will cause its internal energy change to be negative. Think about it. If the system loses energy, right? So let's say the system starts out with 10 kilojoules of internal energy, and something happens and the system, loses some amount of energy. clearly the final internal energy will be less than the initial internal energy. The initial internal energy is what it started out with. Let's say it started out with 10 kilojoules. If something happens and the system lost some energy, then maybe its final internal energy will fall to about 6 or 7, I don't know. And so what you can see clearly is that the final internal energy is less than the initial internal energy. So when you try to calculate the internal energy change, you'll get a negative change in the internal energy. Okay? Right. If, however, the system gained some sort of energy, then its internal energy change will be positive because the final internal energy will be bigger than the initial internal energy. And if you think about it, it's not so difficult to visualize, because if this is your system, let's say this is your system, okay? Energy is going in. Let's call this energy E, okay? If energy is going in, then what you'll find is that the final internal energy will be greater than the initial internal energy. Therefore, when you say delta U, what you will have is that U final, all right, minus U initial must be equal to some positive value. Makes sense? It must be equal to some positive value. However, if you have a situation where energy is being lost from your system, then what you will find is that U final will be less than U initial. So when you go to calculate delta U, okay, when you go to calculate delta U and you say U final minus U initial, it is a must that you will get something negative. Okay? I'm sure you can agree with that. Okay. Now, the internal energy of the system is dependent on a number of things. It is dependent on the temperature, the pressure, the size, right, of the system, and the physical state, and also the chemistry, what we say the chemical substances, which is basically chemistry of the system. Okay, so the internal energy is affected by those factors: temperature, pressure, sample size, all right, that is the reactants, and also the physical state of the system, whether you deal with a solid, liquid, or vapor, and also the chemistry, the chemical nature of the system that you're dealing with. All of these things affect the internal energy. Now, what we should know is that some functions are called state functions. Internal energy is one of such. What do we mean by this state function? Now, a state function is a function or a property whose value depends only on the present state and also the initial state of the system. That is why it's called a state function. It doesn't matter how you get there. We just need to know about your final and initial states. What am I talking about? Let's say this box. Let's say, let me just try to sketch you an image here. Let's say this box is right here, okay? And you decide to take this box and you bring it over here. All right? So basically, you just lift it up and move it over there. Okay, this is the initial state. Let's just call this I. And this is the final state. Let's just call it F. Instead of just moving it directly over there, you could probably decide to take it and put it here. All right? And maybe you decide to take it and put it here. And then you decide to take it and put it there finally. All of that doesn't matter when it comes to state functions. All state functions care about is just the initial and final state. It doesn't matter that you went over here first, and then you went up here, and then finally over to here. It doesn't matter. State functions don't care about that. They only care, or they're only concerned with the final and initial states of the system. So they don't care about that. All right? And those are what we call state functions. Internal energy is a state function. Okay? Now, right. So that's what it is about. And this is a nice little analogy here for those in Jamaica. Internal energy and PV work. We want to get to this. So if there is a change delta x, the value of a state function for a process, yes, is minus delta x for the reverse. Now this is interesting. This is a little bit interesting. Now with state functions, let's say you have a reaction, right? Let's say you have a reaction, A, all right? Let's say A and B is reacting to give you a product P. If this process, when A and B reacts and you get a product, if the enthalpy change for that process, let's not say enthalpy, let's not even go to enthalpy yet. Let's use internal energy. Let's not jump let's not jump over too many things. Okay, so let's say the internal energy change is, let's say, 10 kilojoules, okay, for that process. Somebody might ask you, okay, so A reacts with B to give you a product P, and the internal energy change is 10 kilojoules. What if the product breaks down, right? What if the product breaks down to give you back A plus B? What would be the internal energy change? The internal energy change would be minus 10 kilojoules. So that's what this statement is saying. If there is a change, delta x, in the value of a state function for a process, the change is negative delta x for the reversed process. That's all that is saying. All right? Now, the overall change in the state function is 0 when the system returns to the original function. What is that? What are we saying there? This statement is basically saying that if you make 10 steps forward and 10 steps backwards, then the overall change is 0. That's it. It can cancel all the way out. All right? So it says, thus, the overall change in the state function is 0 when the system returns to the original function. Okay? All right. Now, PV work. We want to get more into some numbers and stuff, right? And to apply things now to actual chemical systems, because we have been building upon the theory, building upon the theoretical understanding of the whole thing. But what about the actual chemical systems? How do we apply all of this? Now, PV work, sometimes referred to as just pressure volume work. Now, first of all, remember, work is equal to force times displacement. Of course, most times we just say force times distance. That is mechanical work. It is the force times distance. Now you're probably wondering, how is it then that a chemical system is able to do work? How is it that a chemical system will apply a force and also travel some distance? How does that work? Okay, I'll show you. Look at this example down here. All right? Propane gas reacting with oxygen to produce steam, right? And carbon dioxide. Look at this. On the reactant side, if you look at the number of moles of gas that you have 5 moles of oxygen gas and 1 mole of propane gas. Okay? So at 5 plus 1 is 6. So you start off with 6 moles. All right? 6 moles. And look at the product side. You have 4 moles of steam, right? Plus 3 moles of carbon dioxide. That works out to be 7 moles. That works out to be 7 moles. So think of this. Let's say you have a balloon. See if I can draw a balloon. Let's say you have a balloon. That is your balloon. So you start off with 6 moles inside your balloon. And then this chemical reaction occurs in your balloon. I am sure you would agree that if this 6 moles turns into 7 moles, you will end up with a bigger balloon. Yes, the balloon would expand in size because now you have more gas particles or more gas molecules inside your balloon. So your balloon has expanded. That is interesting because in order for the balloon to expand, a force must have been applied to the walls of the balloon. A force must have been applied to the walls of the balloon. And that force caused the walls of the balloon to travel backwards. In other words, expand. That force, right? Remember what mechanical work is. It is force times displacement, or we commonly just say distance. This is, what am I writing here? Let me just erase that and fix it. All right. So the work, yes, work is equal to force times the distance, okay, or the displacement. So a force was applied to the walls of the balloon, and those walls traveled backwards a little bit. That is, they expanded, they moved a bit further away from each other. The balloon got bigger as a result. Right? So this chemical system did work. It did some work. Force times distance. Okay? And this is how chemical systems do work. The gases produced during the reaction does the work. That's how it goes. Okay? Now, let's get more into it. Okay, so what we want is some sort of formula or rule that we can make use of in quantifying the work done by chemical systems. That's what we want to derive or formulate. Now, imagine that you have a cylinder. Imagine that you have a cylinder, such as this one. Okay? So this is your cylinder. You have 6 moles of gas starting out with, all right? And at the end of the day, at the end of the chemical reaction, you ended up with 7 moles of gas. Now, that cylinder has a cover. It has a cover, right, which is able to move up or down. That cover, on top of it, there's a force called atmospheric pressure, which is symbolized by that red arrow. Okay, clearly, if you started with 6 moles and then the reaction created 7 moles in total at the end of the day, then it is clear that the cover of the piston would move upwards. It would travel from an initial distance h1 or an initial height h1 to a final height h2. The difference between which is called delta H and is equal to the distance d traveled by the cover. Alright? So we can understand that. Now, we already said that the pressure on the cover, that red arrow, is atmospheric pressure. Now we know that pressure is equal to force over area. If we rearrange this formula, then we can get this one, which says that force is pressure times area. Now, in our previous 2 or so slides, we learned that work is force times distance. What we could do is to take force out of this equation or to substitute force for pressure times area. Just like this. Okay? So this is what we would end up with for work. Work would be equal to pressure times area times distance. Okay? Okay. Now the distance traveled. the distance traveled by the cover is delta H, change in H, H2 minus H1. But H, or delta H I should say, is the same thing as D. Okay? The change in the volume of the cylinder can take place via two mechanisms. Either there's an increase in the cross-sectional area A, or there's an increase in its height. In our case, there's an increase in the height. Okay? Because the piston moved upwards by some amount D. So we know we could substitute right here. We could remove delta H and write delta V is equal to A, right, times D. Okay? We could do a little rearrangement and say D is equal to delta V divided by A. So in this expression, we could remove the D and put this one. Yes? Of course, we could do that. All right. If we do that, then we will end up with this one here. Work is equal to P times A, right, times delta V over A. This A would cancel with that one. And so what you will end up with is that work is equal to P delta V. Okay, so work is equal to P delta V. Now, let's remove some of this. We can make a designation that, look, work is always done by the system. And so we can put a negative sign indicating that work is always done by the system. Now, that negative sign is not something that you need to work out or figure out. It's a designation given to you. It is a given, in other words. So you might be saying, oh, but you made an assumption that work is always being done by the system. What if work is done on the system instead of by the system? What would happen? I am telling you that this negative sign would take care of itself. Because if there is a compression, that is, let's say we started out with 6 moles and then ended up with like 5 moles, for example, meaning that the piston or the cover would have moved downwards, right? Then the volume change would be negative, right? Because the distance traveled would be negative, and so the volume change would be negative. So what would happen is that you would have minus P times minus delta V, which would equal to positive work. Okay, so the negative signs will take care of themselves. You don't have to worry too much about those. Okay? All right, good. Now, look at this same system. All right? Propane reacting with oxygen, gas, of course, both are gases, to give us steam, 4 moles of that, and 3 moles of carbon dioxide. Now, of course, we can see clearly that there's an expansion because we're moving from 6 moles to 7 moles of gas. All right? And of course, if we keep the temperature constant, that is important, right? Because we already know, according to Charles's law, increase in temperature will cause an increase in volume for a fixed pressure, all right, and a fixed mass of gas. So we have to be careful. We have to be careful of that. Okay. All right. Let's see. What is this? Oh, sorry. Okay. Now, delta V is positive and the overall energy change is negative, since W is equal to minus PdV. Now we're talking about this same system here. That is the system that we're talking about. For such a system, let me just erase this mark here. For such a system, you can imagine that if there is an expansion in that, we are moving from 6 moles to 7 moles, right? The volume change is positive. That is, delta V is positive. Okay? The formula has a negative sign on it. Naturally, that is the given. And so the work would be negative. So whenever the system does work, then the work is negative. That is, the volume change is positive. So whenever there's an expansion, that means that the system does work. Now you'll probably be wondering, how is it that the system did work? Well, it did work in applying a force and causing the cover of the cylinder to move upwards, basically pushing back against the atmosphere. That is the work done, force times distance. All right? Now, this is something important. This is something important and interesting. Now, we have been saying that work is equal to minus P delta V. Okay? Now, but look at this system here. Look at this system. How would you know the difference in volume? We keep looking at the number of moles alone. Indeed, we can look at the number of moles and tell whether or not work will be done on or by the system. However, if we assume ideal gas conditions and make use of this expression here, then we can look to the fact that P delta V must be equal to delta nRT. Hence, work is equal to minus P delta V, which is also equal to minus delta nRT. Facts. Okay? And so for this reaction, you could calculate the work easily. Of course, you're probably asking now, but what is this delta N? What is this delta N that you're talking about? Delta N is equal to the number of moles of gaseous products minus number of moles of gaseous reactants. So, for example, this example that we have been using, all right, what is delta N for that example? Delta N is equal to, let's see, number of gaseous products, and don't forget that, is 7. Number of moles of gaseous reactants is 6. So delta N is 1 mole. Okay? Just like that. Okay? Now, look at this example. Hydrogen gas reacting to give you ammonia gas, and hydrogen gas reacts with nitrogen gas to give you ammonia gas, right? Just by inspection, you can see that this is a compression. In other words, the piston would move downwards. How is it that I was able to figure that out? Look, on the reactant side, you have what? 4 moles, right? You have 4 moles of gas. Whereas on the product side, you have 2 moles. If you have that cylinder that we were discussing earlier in deriving the rule for work, and you started out with 4 moles of the gas, and then at the end of the day you end up with 2 moles, then of course the piston would move downwards. In other words, for this reaction, work will be done on the system and not by the system. Okay? That is, you will start out with a large volume and end up with a small volume. In other words, you will start out with a large balloon and end up with a small one. There's a negative change in the volume. That is, there's a decrease in the volume. All right? For this reaction, we can calculate the work easily. We can easily calculate the work. All right? How? Well, we'll say work is equal to, all right, minus delta nRT. Right? Work is equal to, delta N would be, well, remember to put the minus sign, don't forget that. Delta N would be 2 minus 4. 2, which is the 2 moles of gaseous product, minus the 4, which is the total number of moles of gaseous reactants. Put our unit times 8.314, yes, joule per Kelvin, per mole times the temperature. Let's say it was 25 degrees Celsius, which is 298.15 Kelvin. Kelvin cancel with Kelvin there, mole with mole there. Alright, and so when you plug all of that in your calculator, your answer will be in joules. You can plug that in your calculator and you can work that out easily. Alright, you can plug that in your calculator and work that out easily. Okay. Alright. Okay, this thing keeps giving me some trouble. Now, so the volume will decrease, right? And so we said all of this already. So the work is done on the system by the external pressure. Hence, its internal energy will increase. And that's an interesting point. When work is done on the system, its internal energy will increase. However, when work is done by the system, its internal energy will decrease. That kind of makes sense, because if the system starts out with 50 kilojoules of energy inside it, and it does some work, of course, you don't expect that the internal energy will remain the same. In order to do work, you have to use energy. Remember, energy is the capacity to do work. Okay, so if you do work, you would have used up some of your energy. Hence, when a system does work, it consumes some of its internal energy. Okay? Right. If there's no change in the volume, then there's no work. Work is done by gases in chemical systems. Without gases to cause a change in volume, then there will be no work. All right? In other words, the system cannot do work without gases. Gases do the work. Okay? Don't forget that. Now, continue with our internal energy and PV work. Now, note, a system can exchange energy with its surroundings by heat transfer or by doing work. And we said that earlier. Thus, the change in the internal energy delta U is equal to heat change plus PV work. And so what you find is that delta U, which is the internal energy change, is equal to heat transferred plus work done. Now, of course, you can rearrange, you can remove the W, which is work, and put minus PdV, minus P delta V, because we found out earlier that the work is equal to minus P delta V. So hence we have this here. Okay? All right. We can go a little bit further too. We can start to take this part across the equal sign. We can take that part across the equal sign. Okay? When you take that part across the equal sign, you're left with Q over there. So what you find is that Q is equal to delta U plus P delta V. The heat transferred is equal to the internal energy plus P delta V. Amazing. Now, note, Q is positive when the system gains heat. However, Q is negative when the system loses heat. So when heat is transferred from the system or out of the system, Q is negative. However, when heat is transferred into the system, then Q is positive. Now, this part is even more interesting. Look at what is happening here. Q, subscript V means constant volume, is equal to delta U when delta V is equal to 0. And this, all of this, it comes from this expression here. All of this comes from that expression. Let me see if I can show you. So we said that Q is equal to delta U plus P delta V. Clearly, if delta V is 0, then 0 times P is equal to 0. Okay? Delta V being 0, right? Delta V means 0 is basically because if V is, it comes from the fact that V final is equal to V initial, such that when you say delta V is equal to V final minus V initial, you end up with 0. What this is saying is that the volume is constant. If the volume of a system is not changing, it means that its final volume is equal to its initial volume. It means that if you take the volume, if you measure the volume of the system 8 o'clock in the morning and call that the initial volume, if you go back and measure the volume at 12 o'clock in the day, the volume will be the same. So final and initial volumes are the same. So when you say final volume minus initial volume, because they are the same, then you end up with 0. And so delta V becomes 0. If delta V is 0, then 0 times P is equal to 0. So what you find now, if the volume is not changing, Q at constant volume is equal to delta U. So if you can do a reaction inside a vessel, right, where there can be no form of volume change, then whatever heat that you measure, that heat is basically equal to delta U. Alright, so under constant volume conditions, the heat released, right, is equal to the internal energy. And that is what this little statement here is saying. Okay? This brings into perspective another term called delta H, which is the enthalpy change. Enthalpy change is the heat at constant pressure, or the heat change at constant pressure. Alright? So Q at constant pressure is equal to enthalpy change. Enthalpy change, the simple definition, is the heat transferred at constant pressure. Okay? Heat transferred at constant pressure is equal to delta U plus P delta V, which happens to be equal to the enthalpy change as well. And hence this can bring us to a more complicated definition. Right? The more complicated definition is that enthalpy is the sum of the internal energy plus the product of pressure and volume. Alright? Yes. Enthalpy change is sometimes referred to as the heat of a reaction, or enthalpy change of the reaction. Okay? And we said that enthalpy change is just a constant pressure heat, or the heat transferred at constant pressure. However, a more complicated definition is the sum is to say that enthalpy is the sum of the internal energy, alright, plus the product of pressure and volume. Alright? Okay. Now, enthalpy. Enthalpy change is very, very important. And it is very important because most chemical reactions in even biological systems occur at constant pressure. When, for example, you go inside your lab and you do your experiments, most of these experiments are being done under constant pressure conditions. You're doing them in the lab under atmospheric pressure. And atmospheric pressure don't fluctuate a lot. Okay, so your pressure is constant. So most chemical reactions occur under constant pressure conditions. That's the reality. Now, in assessing the enthalpy change of a reaction, and enthalpy is a state function, what we do is to take a sum of the enthalpies, or the enthalpies of the products, of course considering their stoichiometry, reaction stoichiometry, and subtract from that the sum of the enthalpies of the reactants, of course considering their reaction stoichiometries. In other words, what we do is to say enthalpy change for a reaction is the final enthalpy minus the initial enthalpy. The final enthalpy is the sum of the enthalpies for the products, considering their reaction stoichiometries, of course, whereas the initial enthalpy is the sum of the enthalpies of the reactants, of course, considering their reaction stoichiometries. Now, under laboratory conditions, and in cases where gases are not involved, it is important to note that the enthalpy change is basically equal to the internal energy change. Basically equal to, I'm not saying it's equal to, it's basically equal to. Because if you don't have gases, then the PV component, pressure times volume component, is very small. Right? And sometimes people say, oh, it's negligible. You could ignore that. Okay. Now, when delta H is positive, the process is said to be endothermic. That is, heat is absorbed. However, when delta H is negative, the process is said to be exothermic. Right? That is, heat is released or emitted by the system. Okay? Note also that delta H is a state function, as we said earlier. That is, and remember we said, state functions only consider or only take into account the final and initial states of a system. Alright? Now, we want to get into talking about isothermal and adiabatic changes. Okay? And we'll take our time and drift into these. Now, an isothermal process, remember iso means the same. Thermal, once you hear thermal, you should be thinking about heat. Isothermal, therefore, means same temperature or constant temperature. Alright? Now, an isothermal process occurs within a closed system. That is, it can exchange energy but not matter with its surroundings. And of course, earlier we defined what a closed system is. So an isothermal process occurs within a closed system. Right? So let's say that again. An isothermal process is a constant temperature process. Iso means the same, thermal means heat. So isothermal means constant temperature. And an isothermal process occurs in a closed system. As we defined earlier, a closed system is one that can exchange energy but not matter with its surroundings. An isothermal process can occur in a closed system with a diathermal boundary. Diathermal means that the boundary allows heat energy to leave and also. Let's say, for example, you're in the lab and your manual says that you are supposed to conduct your reaction at 30 degrees Celsius. You could think of turning on your hot plate and you take the beaker, you put the beaker on the hot plate, bring the temperature to 30. When it's going over, you take it off, put it back on. But that is difficult and not so practical. And of course, your temperature might go over, it might fall too low. An easier method would be just to get a water bath. Alright? And put your system, which would be your beaker, inside that water bath. Set the water bath to the 30 degrees Celsius, and the water bath will maintain the temperature for you by switching on and off and keeping the temperature still. Now, how is that possible? Well, whenever your beaker, which is your system, gets too warm, right, the water bath will try to cool down and heat would move from your system into the water bath. However, whenever your system started to get too cold or too cool because it's losing too much heat, then the water bath would add some energy to your system. So the boundaries of your system would have to be diathermal, allowing heat to move in both directions in order for for the isothermal condition to be met. Okay, let us erase here so you don't get too confused. Now, for an isothermal process, delta T is equal to 0. That's what constant temperature means. T final is equal to T initial. And so when you go to say T final minus T initial, you end up with 0 because they are the same. There's no change. Alright? There's no change. Alright. Let's say that again. We should note that when we're dealing with an isothermal system, that is where delta T is equal to 0, delta U is also equal to 0. Okay? Delta U is also equal to 0. And so the first law of thermodynamics can be modified. Well, the equation could be modified a little bit, because what you have is delta U being equal to 0, and so you could separate these two. Okay? That is, let's show you what I'm talking about. Let's show you what I'm talking about. If we say that delta U is equal to Q minus P, alright, delta V, then 0, if delta T, and this is when delta T is equal to 0, isothermal conditions, then what we have is 0 is equal to Q minus P delta V. Therefore, Q is equal to P delta V. Okay? Right. And that is what we have going on here. Next, if we picture a boundary that isolates the exchange of energy and matter, then we're talking about an isolated system. And so there cannot be exchange of heat if we're dealing with an isolated system, because remember earlier we defined the isolated system as one in which no energy is exchanged with the surroundings and no matter is exchanged with the surroundings. So that's what an isolated system is. Although the system is thermally isolated, it can still do pressure volume work. And this is really the definition of an adiabatic system. An adiabatic system is one in which no heat, or let's say energy, because heat is a form of energy, no energy or matter can be exchanged with the surroundings. However, the system can still do work. All right? Now you're probably wondering, how is that possible? What is going on? Well, imagine you have a system. This is your adiabatic system. If you have some gas molecules, all right, those gas molecules can still expand and fill the container, of course. If they are expanding, then that is work, all right? Of course, because there's an increase in the volume, all right, and the pressure is constant, so there's an increase in the volume. However, there can be no exchange of heat with the surroundings. There can be none of this. That is not allowed for an adiabatic system. There's no exchange of heat. Now, we're not saying that inside the system you don't have heat. Heat is there, but there's no exchange of heat with the surroundings. Okay? So, heat change is 0. Okay? However, there can be work. The system can do work. There can be expansion, there can be contraction. Okay? So, for an adiabatic system, delta U is equal to W, which is equal to minus P delta V. Okay? For an adiabatic system. Now, of course, we'll see more on that in other lectures.